So the title of the presentation is Analyzing Quantum Approximate Optimization Algorithm. And it's kind of really going into the structure and understanding better what is happening there. So this is joint work with these people there. So I was mainly working with Sujay, Martin, and Marco here. And so I'm working at Forschungszentrum Jülich at the Institute of Quantum Control. So let's get started. So I want to kind of have a little bit kind of a high-level motivation for this talk. So it's kind of analyzing this particular variational quantum algorithm. And my point is really this whole kind of field of variational quantum algorithms, it's kind of really at its start. So we have very simple algorithms which work in very high-dimensional spaces, which we barely understand. And this is kind of, the motivation is really, on the one hand, to have a better understanding and really apply symmetry tools to this. And by doing so, also refine the existing symmetry and computational tools to analyze these systems. So this is the high-level motivation. So I will kind of, on this high level, at the end, I will also kind of say a little bit how I think a little bit more about this. But this to kind of get started. So I will have kind of different parts to kind of make sure that nobody falls asleep, or if they fall asleep, if they see this, then they can kind of start, oh, now something slightly different starts. So in the beginning, I want to just make sure that everybody's on the same page. So what is the problem, this maxcut problem? What is QAOA, and what are these different ansätze to kind of see that we get started, everybody understands the problem, and then we move on from that. So, short recap, what is the maxcut problem? So we have a graph. You might or might not be able to see it here. And throughout the talk, the vertices are usually V and E, are the edges. And the maxcut problem is the following. We want to divide the vertices here in this picture into black and white vertices so that the number of edges between black and white vertices is maximized. So, and it's kind of here visualized with this red kind of path here. This is like a cut. So, and this is actually also a maximal cut. This kind of has the value of 5. So, because we have 5 edges which go from black to white. And this similarly simple problem is actually NP hard. So we are not talking, so I'm talking about the optimization version. But this problem is kind of quite natural. So the physics version of it is just, we want to find the ground state of an Ising Hamiltonian. So these problems are equivalent. So this is a maximization problem, this is a minimization problem, but if you solve this one, then you solve that one, and the other way around. So you can kind of have this picture here with some Ising kind of Hamiltonian on the same graph. But it's important, this maxcut problem, given a graph, you want to solve it. And obviously for this toy example, you can just try all possibilities. But you might wonder, so this problem is actually quite important also in industry. So just before I go to the quantum realm, so what is actually our competition, to be clear? So there have been actually, so some people might know this quadratic optimization problems, which are very much kind of, maxcut is a special case. So this has been some very nice recent paper on the classical side. And my understanding that 10,000 vertices are usually not a problem for solvers, not for arbitrary graphs, but for graphs which actually appear in practice. And so you can now think how big your quantum computer need to be to actually start to compete with this. So, and then there's this famous algorithm by Gomans and Williamson, and they do like an approximation version. You don't want to find the best maxcut, but you want to be as near as possible to it, and they have this approximation ratio. And they have this weird number, and it's actually not known if you can be a little bit better than this, but not much better you cannot be, because then you will be also NP hard. So this is the classical competition. And I think it's important to remind yourself about this. So now QAOA by Farey, Goldstone, and Goodman is an archive which was, is my understanding, was never published. So what is this algorithm? you take your edges in your graph and put some ZZ interaction into your circuit, and then at the end you have X interaction on each of them, and then you have one kind of angle for all of these colored ZZ ones and one for the X. Formally, you can write this corresponding circuit here, and you have multiple layers of this. And what you're doing, you just, with a classical optimizer, try to optimize the angles. And then at the end, you measure, and then you hope to find the ground state. So it's kind of a very simplistic algorithm. It's kind of just a feedback optimization in principle. So there's a slightly different version I don't want to talk here, which has some classical preprocessing. This feedback version has no guarantees at all. In my opinion, it's a little bit mysterious why it should work at all. So I think this is very important if you don't kind of understand how this algorithm works. So you might kind of later kind of get a little bit lost. So we have these Z interactions here with potentially for each layer different angles. And here we have the XX. So the P is for the ZZ, the M is for the X's, and you have multiple layers here. So you might have many, many layers, and then you just optimize these angles. Okay, good. So now we will kind of in this presentation consider two ansätze. The standard one, which kind of is in this picture, and what we can call the free or multi-angle ansatz. So now you see I have different colors for the different ZZ interactions here. And this is because we now allow separate angles for them and also separate angles for the x-axis. So in a certain sense, this right picture, you're just allowed to, as Hamiltonians, have Pauli strings. Here you can also sums, because we have the sum over all ZZs and the sum over all XX. So, and formally written down, these generators are here again for the standard model. So we have two generators, which then potentially are repeated. And here we have kind of just the constituents of the sum. And we will see that this model with the free ansatz is a little bit easier to analyze, and we have much better results for that. And the larger part of the talk will be what we know about the standard ansatz. So you can think about many more ansätze, but for this presentation, we consider only these two. So now we set up the stage. We will now look at the free mixer case. So we will actually realize that for all graphs, there are actually only 6 family of Lie algebras you can get, which is kind of surprising as there are so many different graphs. And we kind of tell a little bit about what bases these Lie algebras have and what representations, and a little bit hint about how we prove things. This is one of the first results we got. So we kind of distinguish between the path graph, the cycle graph, and these 3 types of bipartite graphs, and all other graphs which we call archetypal. And you see that the cycle graph is sometimes bipartite, sometimes it isn't, and the path graph is always bipartite. And we get here these orthogonal Lie algebras, or direct sums for path and cycle. We get this exponential Lie algebras for these bipartite ones, and then we get for all the rest, we get this very simple structure. You can kind of think, so this is actually the most interesting case for the applications. You can think you have like 2 big blocks, which kind of fully controllable in this block independently. And I would say this result is a little bit surprising, that only these possibilities appear. And it's kind of really, what is kind of really a feature, that these Lie algebras are kind of polynomially large, and all the others one exponentially large. So one sees the separation. So we can actually write down explicit Pauli string basis for all of these. So the bipartite case is a little bit annoying, but the basis is kind of easy to characterize. And I think in future we will always, if you say bipartite case, we mean not cycle or path graph. And also here these don't include them. So we can have very explicit representation here for these. So a little bit of the proof techniques. So I cannot go into much detail. So probably we sit here for days until we explain all the subtle details. So the first thing to understand is that we have these 2 symmetries, identity and x tensor n, which are the only ones. which kind of guarantees that we get this block structure, as I mentioned. So this if you think for 5 minutes, you'll realize that. And then one proof technique, so you can always compute commutators and guarantee that you have certain elements, but at some point you will write pages of commutators and get kind of confused. So there is one very neat technique, is about maximal subalgebras. So this subalgebra H is a maximal subalgebra if there's some maximal subalgebra of G, and also proper here, if there's something in between that it needs to be either equal to H or G. So, and people have analyzed these maximal subalgebras, they work at Dynkin and so on. It's kind of very useful tool in the sense that if you have an element in G, which is not in H, and you add it to H, then you will get G. There's no other possibility. And this you can kind of very effectively use if you know that certain kind of pairs are kind of maximal subalgebras. So here's some example. So we have like a maximal chain here. So this is kind of all the Pauli strings which kind of do the same on the upper block and the lower block here. And we don't allow the identity in these blocks. So we get some SU n minus 1. But then if you also have minus 1 and minus in the block of all Pauli strings, you can kind of think as the previous one, but with some special element, you get actually these independent SU2n's, and then if you add some other element, you get this, and this is actually maximal in SU2dn. So you have some natural chain, and this particular chain actually, at some point in the proof, it's kind of critical that we kind of establish this. So I think this was shortly mentioned already with respect to some question. The other thing is, if you act on some block irreducible, you want to know if like an S or SP and so on, and you get this Obata condition, which is essentially the unitary version of the Frobenius-Schur indicator. And then in low dimensions, sometimes you just write down some explicit isomorphisms, which for the SO2n plus 1, it's irreducible SO2 to the n, and you think you can kind of really establish the isomorphism. In principle, you need to check all the commutators, is everything fine, but these have been known for quite a long time, and they are kind of critical in this perfect cycle graph. So actually, we actually almost for all things, except for the perfect cycle graphs, we actually have 2 mostly independent proofs of everything. And it's kind of 12 double column pages, which you can think it's kind of takes a long time. So I want to kind of the most high level kind of idea. So in the first one, which I would say is a Lie-algebraic induction proof, and it's really a subtle proof. So you're not allowed to prove too much, because then you prove something which is not true, and you need to be very careful here. And the main idea is to kind of make a basis change. So we have seen our generators here of this form. U and V are for this kind of isomorphism here, kind of greater or equal to 2. And we separate the ones which have a 1 in it. And you can kind of make some basis change so that this one is transformed to ZV, and this one is transformed to this operator, which we actually have seen like on 2 slides ago. And then it just doesn't work because we have this not isomorphic blocks, and at some point you get a little bit kind of confused. So we actually work for the induction proof with slightly enlarged Lie-algebras, which are kind of motivated by these operators. We add some ZW for suitable sets, and they have the nice properties, and you can kind of make the induction work. So it's kind of a very high level version. And the second proof is kind of much more kind of working on Pauli strings. It's more like a saturation proof. It's, for one thing, it's a lot about counting Pauli strings. So because then you establish a dimension of the Lie algebra, which kind of gets you already quite far. But it's kind of the main idea is that without changing the Lie algebra, you can kind of think of adding an edge and the corresponding generator. And in some cases, you can do that, and then you argue about that actually all connected bipartite graphs, which are not of this kind of cycle or path graphs, actually, you can add more and more edges. At some point, you get the complete bipartite graph. And then you establish what is going on with the complete graph. And for the non-bipartite cases, you just get the complete graph. So there are some technical ways to kind of establish and that you get all the things, but this is the high-level way of kind of proving this. say, okay, so what? We have this classification of 6 classes of Lie algebras. What does this tell us? And now we will have kind of one high-level consequences, kind of really implications for this free ansatz. So we will kind of restrict us to these graphs which are not bipartite or cyclic graphs, which we call archetypal graphs, and where we know that this Lie algebra is like this. And now we establish something that there will be barren plateaus here. And this is kind of based on earlier work of Martin and Marco. So for that, we need to talk about designs, as we have seen before. So we need to talk about what is an approximate unitary 2 design. And essentially, it's behaving like the Haar measure up to second moments. So this is kind of the shortest version, and I don't need to kind of talk too much because David already kind of talked about this in a slightly different kind of version. And so now the point is we need as a condition for the theorem that we have a epsilon approximate unitary 2 design, which kind of tells us that the circuit is deep enough. So if you have a very short circuit, the establishment of the barren plateaus will not work. So you need to kind of have a deep enough circuit, and this kind of captured by this condition here. So this is kind of the first thing. And now the theorem states the following. We get exponentially vanishing partial derivatives of our kind of cost function. The assumption is that we have these archetypal graphs, and this describes the number of edges. We have enough layers so that we get this approximate 2 design, and now the variance of our cost function will be, on average, kind of be exponentially vanishing. So what does this mean? You have an optimization problem, but in every direction you look, everything looks completely flat. So what do you do in this case? I think you cannot do much in this case. So one needs to kind of say this is on average, this statement here. So on average, every point you are, it will look like you're completely flat. So gradients will not help you, and essentially you're kind of in a high desert, don't know where to go. So this is the statement. And essentially this uses some earlier result of Martin and Marco, and the essential clue why this works is because the Lie algebra is exponentially large. So we want to have exponentially large Lie algebras because we want to do quantum computing, but here it's kind of really hurting us. So this mentioned already, it's kind of, on average, we have flat optimization landscape. So what we don't know right now exactly, how many layers do we need to establish this? So in general, I think there is no theorem for this, but I think a lot of people are investigating this kind of topic in a slightly different fashion. And my feeling is probably polynomial or even linear should be enough. So one needs to kind of prove it exactly for these generators and so on. One needs to probably get some properties. So I think this is, I would say, very bad news. So right now, this is only for the free mixer case. We have a very short kind of introduction to symmetry and Lie analysis. I want to just highlight some points. I will not go in any detail, which I think important. So we have been talking about generators and Lie algebras. So it was mentioned already in Thomas' talk. So we can talk about what is the commutant. It's just the matrix that commute with certain set simultaneous of matrices. And then we can talk about the commutant of our generators. And actually here it doesn't matter if we take the generators or I times the generators or the Lie algebra. So usually we want to go from the generators because we don't want to first build the Lie algebra. I think another object interesting to think about is this matrix algebra A. It's kind of the matrix algebra, complex matrix algebra generated by the generators. And C and A will have some nice connections, with the expert probably know. And then we are sometimes interested in the matrix that commute with all other matrices in a certain set, which called at the center. So these are kind of objects which are kind of interesting to think about. And I repeat them here. And now we get some immediate theorems. And as I said, probably people with representation theory background or algebra background is kind of established by Emmy Noether. So we can we know that the commutant of A is C, and the other way around, and the commutant of A, and then taking the commutant again, we get A back. So this is the usual double commutant property. But I think this property is actually more interesting. So the centers of A and the centers of C are actually equal, and they are just the intersection of the both, which will be very important in a second. So it's important to realize that the double commutant property doesn't hold for the Lie algebra, actually. So if you take the double commutant of the Lie algebra, you don't get the Lie algebra back, which might...
You get the smallest matrix algebra that
yes,
comprises the Lie algebra.
you get A back. So, so probably for some of you, this is kind of well known. So I think this is very important. And now we can shortly talk about isotypical and irreducible decompositions. So essentially, the isotypical ones collect the same irreducible type together, and then it's further refined. But the refinement actually depends on if you're acting with A or C. The isotypical components don't matter. You can kind of compute them via A or you can compute via C. Probably C is the better way to do this. And you have actually this duality between the multiplicities and the dimensions. So the multiplicity in one of the cases is the dimension in the other one, and so on. So it gives you some way to compute something of the action of A via C. And you can write this in kind of this tensor product form. So this also kind of gives you some decomposition of the Lie algebra. And this is kind of thinking of some set of matrices which kind of acting irreducibly. But it's important to realize that neither the Lie algebra or this kind of G lambdas are uniquely determined by C or A. So you could potentially have different ones there. So because you could have different irreducible Lie algebras acting on that space. So I don't want to dwell on this so much. The other thing I want to mention is the reductive decomposition, which is kind of a little bit orthogonal to the previous discussion. It's really decomposing the Lie algebra into its center and direct sum of its simple components. So, and the simple components obviously need to compute with each other for different components. And you can either interpret this like an intrinsic vector space decomposition of the Lie algebra, or you can kind of thinking of embedding some abstract Lie algebras into larger ones. So this is usually most difficult to actually compute in practice. So now we go into the rabbit hole of the analysis of the standard ansatz. So if you followed until now, it's already quite good. So, so just repeat, we have these two generators. So I have this house graph is our favorite example. We have these two generators, and you can think, oh, there's some block decomposition. You get blocks of 10 dimension, 5, and 1 dimension, and you get this reductive decomposition here. So this you can, in this simple example, obviously by brute force, you can establish this. And what is interesting, if you start in this block, you never leave this block, obviously. Because, but the good thing is we know that there's a solution in this block. This is essentially the same information. I complement this information from the standard case to the free. So actually here the commutant is 2-dimensional, but here it's 6-dimensional. So because we also get kind of these 6 blocks. And so we see that kind of the blocks and the Lie algebras are kind of related. But there's one important caveat here. Actually, the center has support on all of these components here. So naively, we would think the center is hiding in these 1-dimensional blocks, but it doesn't. So it's a small side remark, but it's important to not fall into this trap. So now we will kind of approach kind of the structure of the commutant or the symmetries kind of in a certain step. So we've introduced kind of what people call the natural symmetries, or what we call the natural symmetries. So what are the natural symmetries? Obviously, you have a graph, you have automorphisms of this graph, which should be kind of a symmetry. And then we had also this identity and X tensor n. These are also symmetries, which are quite natural, and they are in all of the examples they appear. So therefore, we built this kind of, yes, I should explain what this zeta is. So this maps permutation to the corresponding action on the Hilbert space, on the exponentially large Hilbert space. And then we have kind of this this group of natural symmetries is kind of like a direct product because they commute with each other of all the automorphism acting on the big Hilbert space with identity and x tensor n. So this is the group of natural symmetries. But then we are more interested in the linear space by them, spanned by them, which could in principle have a lower dimension. So they could be linear dependent in principle. And these are part of the symmetries. So this we can establish. And now in the house graph, we actually, the automorphisms are kind of the identity and this weird permutation here. And we get actually all the things we get. And it's kind of, these act on the vertices you see kind of, and also this x and x tensor and x on this. And so we get this kind of orbit here under that. So these are the natural symmetries. So obviously if we define the natural symmetries, we will immediately talk, are these all of them? And the answer is no. Now we will talk about the symmetries which are non-zero symmetries not contained in the natural ones, which we call hidden symmetries. And so I want to kind of talk about this table a little bit to kind of, so we can actually describe the symmetries by a certain set of projectors. I don't write them out. And for the one-dimensional, these are kind of, the one-dimensional projector, you can write them with respect to these states. So we, as before, I mentioned this before, we have like the 10-dimensional, the 5-dimensional, 1-dimensional, and so on blocks. And this is kind of the parity-superselection rule. So the first three are in the plus and in the minus block. And for the one-dimensional, these are kind of the corresponding vectors. And then I repeat here all the symmetries, the natural ones, plus P3 and P6, which then build all the symmetries. So these are weird kind of symmetries, which are kind of, in many cases, are kind of one-dimensional, which appear. So we have seen that in the example. And people who know what quantum many-body scars are, this is very much related to this topic, because there they also look at one-dimensional symmetries, which appear in addition. So the picture is the following. We have this kind of quite automorphism symmetries. We have this identity x tensor n. These are quite natural. But unfortunately, the picture is slightly more complicated, which makes our life quite more complex because we get a lot of variety now with respect to different graphs, which might have these additional symmetries, and we have not so an easy way to understand what is happening. Based on this, we are looking at certain symmetrization operations, symmetrization with the Z2, symmetrization with the automorphism, and then symmetrization with both of them, which is kind of the natural symmetrization. And we can kind of, from the unitary group, we can do symmetrization, and we get this U net, which kind of reflects these natural symmetries. And we can do from the free generators, we can do the same thing. And now, for the house graph, we get this kind of picture here. We get certain inclusion relations. So we have seen the free Lie-algebra before. We also understood the standard. Here's another ansatz, which is in this case equal, so you can kind of ignore this. But we get here certain kind of inclusion relations with these arrows. And what is that this G naught has exactly the symmetries from the natural symmetries, and it's kind of building an upper bound to the standard Lie-algebra, so kind of, which kind of we want to know about, but we now will talk a lot about to characterize G naught more, so that we get kind of like an upper bound of understanding what is happening. So and we get now this kind of inclusion relation that, as I mentioned, and then inversely for the symmetries, and we can actually, there's some relation between G naught and U naught here. So we get actually two more elements for these archetypal graphs corresponding to these projectors. And we see that there's just two U1s here. I think one can, it's kind of a little bit hidden here due to this weird notation here. But essentially, we have two more abelian freedoms in here. So in general, these will be quite complex, how they look like. But I think we have like a good theory to actually characterize this G naught very precisely. So now comes where we kind of, for this G naught and the natural symmetries, we can actually characterize the blocks nicely. So abstractly, this group acts is represented as this kind of group I introduced before. And we have a very cool character formula for this combined group. Without going in the Hilbert space, we can actually compute the character of this representation. And the formula is surprisingly easy. So we have pairs of this S2 and the automorphisms. And the character is actually 0 in many cases. But it's kind of characterized by 2 to the power of the second C of the second element. And this is actually in the cycle decomposition of this permutation here. C denotes the number of cycles. And so this case is if this is the identity permutation and this other condition is kind of fulfilled. And we actually, if not all cycles are even length, then we're in this case here. So this is this additional condition here. So this is kind of really practical way to kind of compute characters. And I think it's probably not so difficult to kind of figure out that this is the right formula. So also the proof is not more complicated, but it's very cool because all the kind of our natural symmetries, we know how they act on the big space without ever going to that space. So what does this give us? We can actually compute the dimension and the multiplicities of each block with respect to this G0. And we have some, so obviously the dimension is given by this kind of version of the character, and we have this general kind of formula to compute the multiplicity from the characters. And we get back what we knew already, that we have 10, 10, and 6, and 6. So if we go back to this thing here, we already knew that it's 10, 6, 10, 6 here. But this gives us an efficient way to compute this kind of, beyond this kind of trivial example. And the dimensions here are all 1. So this house graph case is a little bit special that is multiplicity free. So which kind of says the irreducible and the isotypical decomposition are kind of the same. So and from there we have some kind of trivial consequences. So for the so this is kind of the trivial representation, and we know we have now a formula. This corresponds to the biggest block, which we are kind of interested in. And if the automorphisms are the full symmetric group, then we have this very simple formula. So we get a very small block. If the automorphism group is trivial, then we get this exponentially large block, and we have some cases when we know something about the automorphism group. So let's go back like a level higher. So what does this what are the implications for the standard ansatz? So we characterize this thing, but we want to actually know what's going on about this one. So they could, in principle, smaller the blocks. So we have not a direct way to compute them in general, kind of like with this symmetry case. But now we were kind of wondering, okay, so how much smaller are they usually? And now we go to this case of asymmetric connected graphs, which are kind of, in our terminology, also archetypal. And we immediately know that this here holds. So we know that G standard is kind of contained here. But now we compute this gap here. So this is what we know from G0, and this is what we compute by brute force for the G standard. And we want to know how big is this gap in general. And for up to 5 qubits, there are no asymmetric connected graphs. And for n equals 6, I hope I did not mistake, but I think there are 8 asymmetric connected graphs, and the gap is always 0. For n equals 7, we get actually a gap of 0 and 1 with these frequencies. And for n equals 8, we see that almost all of them are kind of a very small gap, and then we get up to 9 gap here. So I think this is not the only data we have seen. This is what we included in the paper. For us, this is kind of a little bit the basis that, okay, so obviously this data is not enough to kind of prove anything. So the gap could kind of grow exponentially with n. It's not ruled out here. But from the other data also we have seen, we are conjecturing now this gap stays actually small. We have this conjecture, stays small, and then we have this 2 potentially, but it's not the only ones, 2 bleak options. So all relevants stay in a polynomial subspace. So then we have classical simulation. And here we have this additional assumption that, so we know now about we conjecture that the block is very big. So we need to assume that we have full control there. So we fully explore this exponential subspace, similar arguments as for the free mixer case will give us also barren plateaus. Then we come to the conclusion. So what are the take-home messages? I think symmetry analysis allows us to better understand variational quantum algorithms. So I think this is very important. So it's an important tool, and our computational and theoretical tools, I think during this project took a big leap. So we can kind of compute much bigger examples we could compute before, understand before. And so we know that the free ansatz has barren plateaus, and in my opinion means it's not practical. We conjecture the same applies to standard ansatz. So in my personal opinion, I'm not really sure if QAOA is such a good algorithm. So obviously we know there are kind of probably hundreds of papers in the last year on this. But okay, so there are some loopholes, as also David mentioned, about smart initialization and so on. So on a more general note is this paper which I was not involved, which kind of makes the general case of variational quantum algorithms, so that you might kind of have the same issue in general, that either it's classical simulable or you have barren plateaus. So my feeling is also this can also affect large-scale numerical feedback optimizations in quantum control. So because it's a very similar setting. And my point is also a little bit, people kind of have these claims about variational quantum algorithms, but it's very little that is actually proven there. So we need to manage a little bit expectations here. You cannot say, oh, powerful algorithm which can solve NP-hard problems, so which you sometimes hear, which is not really true. So this slide I need to put up because they made me, the different sponsors. But we are also happy to have this funding by HPCQS and Pasquant, and we have a lot of also funding from BMBF and also from ML4Q. So thank you.